All right, today we are going to crack the code on one of the most fundamental building blocks of life, carbohydrates. We're going to start from scratch, building them up from the ground floor, piece by piece, and you'll see how these super simple sugars can become some of the most complex and, honestly, most important structures in the entire natural world. So, let's just jump right in with a little puzzle. Think about these four things: regular table sugar, a potato, a piece of paper, and a glass of milk. I mean, they seem completely different, right? One's sweet, one's starchy, you write on one, you drink the other. But what if I told you that chemically, they're all cut from the same cloth? And here's the secret. They are all built from the exact same simple Lego bricks. This is the one big idea you need to grasp today. If you can understand the shape of these basic bricks and the way they snap together, you'll understand the whole world of carbs, from the honey in your tea to a giant redwood tree. Okay, so let's get to it. We'll start with the absolute basic blueprint. What even is a carbohydrate? Now, I know this definition looks a little intimidating, but don't worry, we can break it down. Polyhydroxy. All that means is poly for many, and hydroxy, which is just those little OH groups you see. And the other part, aldehyde or ketone, that just tells us where one specific carbon-oxygen double bond is. So really, a carbohydrate is just a chain of carbon atoms that's decorated with a whole bunch of OH groups and one special C double bond O group. That's the blueprint. Simple as that. So, if carbohydrates are the big, finished Lego creations, what are the individual bricks? Well, they're called simple sugars, or to use the scientific term, monosaccharides. Think of it like a family tree. At the very bottom, the foundation of everything, you have the monosaccharides. These are our single Lego bricks. Now, when you link just a few of them together, say 2 to 10, you get what we call oligosaccharides. But when you start linking hundreds or even thousands, that's when you get the giant structures, the polysaccharides, like starch. But it all always comes back to that first single brick. So these bricks of ours, they basically come in two main flavors, aldose and ketose. And the only difference, literally the only one, is where that special carbon-oxygen double bond, the carbonyl group, is sitting. In an aldose sugar, like glucose, that group is at the very end of the carbon chain. But for a ketose sugar, like fructose, it's somewhere in the middle. This is the first, most basic way we sort our bricks. But of course, it doesn't stop there. Our little Lego bricks can also be sorted by other things, like their size and even something we call handedness. Let's check it out. First up, size. This one's easy. It's just about counting the number of carbon atoms in the chain. A 3-carbon sugar is a triose. A 5-carbon one is a pentose, like ribose, which you've probably heard of because it's a key part of our RNA and DNA. But the most common ones by far are the 6-carbon sugars, the hexoses. And that group includes some very familiar names: glucose, fructose, and galactose. Okay, next up is this idea of handedness. This is super cool. Most sugars are what we call chiral, which just means they exist in two forms that are perfect mirror images of each other, kind of like your left and right hands. So how do you tell them apart? Well, you find the chiral carbon that's furthest away from that main carbonyl group, and you look at its OH group. If that OH is pointing to the right, it's the D form. If it points left, it's the L form. And here's the trick to never forget it. If the OH is on the R, right, it's the D form. Easy, right? And what's wild is that in nature, almost all the sugars that matter for life are the D form. Now, this brings us to a really important idea. Tiny little changes in how these OH groups are arranged can create totally different sugars. And when you have two sugars that are identical in every single way, except for the direction of the OH group on one and only one carbon, we have a special name for that. We call them epimers. And this is the perfect example. Take a look at glucose and galactose. They are almost identical twins. Both are 6-carbon aldose sugars. But look really close at carbon number 4. See it? In glucose, the OH group points to the right. In galactose, it points to the left. That is it. That one little flip is the only difference between them, but it's enough to make them totally distinct molecules that our bodies use in different ways. So up to this point, we've been drawing our sugar bricks as these nice, neat, straight chains. But that's not actually how they look in the real world, especially not inside a living thing, which is mostly water. In reality, they do something pretty amazing. Turns out, these long, floppy chains are not very stable floating around in water. They're kind of vulnerable. So, to get more stable and protect themselves, they spontaneously fold up and twist around to form a much sturdier ring shape. And this process actually has a name. It's called mutorotation. For sugar like glucose, what happens is the aldehyde group way up at carbon number 1 reaches all the way around and forms a bond with the hydroxyl group down at carbon number 5. It's almost like the molecule is biting its own tail to form a closed loop. And the end result of this little reaction is this beautiful, stable, six-sided ring. We call this a Puranus ring. And this is the form that glucose is almost always in when it's dissolved in water. It's just a much lower energy, much happier, and much more stable way for the molecule to exist. Okay, so we've got our bricks sorted. We know how they like to curl up into stable rings. Now it's time for the really fun part. Let's start snapping them together to build something bigger. When you link just 2 of our sugar bricks together, you get a disaccharide, and I guarantee you know these names. The lactose in milk, that's just a galactose brick linked to a glucose brick. Sucrose, which is plain old table sugar, that's glucose linked to fructose. But I want you to pay really close attention to that column called linkage type. The specific way the bricks are connected, whether it's an alpha bond or a beta bond, is a tiny detail that's about to become incredibly important. So, what happens if we don't stop at 2 bricks? What if we link together hundreds or even thousands of them? Well, then we enter the world of polysaccharides, the true skyscrapers of the carbohydrate world. And this right here is where everything we've learned comes together. The 2 most common polysaccharides on Earth are starch and cellulose. And guess what? They're all just massive chains made of glucose bricks. So what's the difference? It all comes down to that linkage. Starch uses what's called an alpha linkage, and this forces the chain into a loose spring-like coil. It's perfect for storing energy because our enzymes can easily get in there and snip off the glucose bricks. But cellulose uses a beta linkage, and that one tiny change forces the chain to be perfectly straight and rigid. And these straight chains can then stack on top of each other like planks of wood to form incredibly strong fibers. And that leads us to this absolutely mind-blowing fact. A potato is basically just starch, a coiled-up chain of glucose that we use for energy. A tree trunk is mostly cellulose, a rigid stack of glucose that provides structure. The building brick, glucose, is identical in both. So the only real chemical difference between a soft, edible potato and a hard, woody tree trunk is the direction of one single chemical bond, repeated over and over and over again. I mean, just think about that for a second. One tiny chemical flip is the difference between food that fuels your body and a material strong enough to build a house with. It just goes to show you how nature uses these simple repeating patterns with just the slightest variations to create this incredible diversity we see all around us. It really makes you wonder, right? What other giant secrets are hiding in plain sight, just waiting in nature's simple patterns?